Hello, this is Eric Strong from the Palo Alto VA and Stanford University. This is the 15th lecture in this course on understanding ABGs, and the topic is alternative approaches to acid-base analysis. The learning objectives are first, to be familiar with the historical background behind the three major approaches to acid-base analysis, and second, to understand the general principles of both the base excess and Stewart approaches, and to be able to compare them to the traditional approach that has been presented in this course. I'm going to start the lecture with a brief timeline of the evolution of our collective thinking about acid-base physiology. You will see later that this is important in understanding the three general approaches to acid-base analysis that exist today, as the fundamental changes that have occurred in our approach to acid-base physiology are largely a consequence of the evolving definition of what constitutes an acid and a base. Modern acid-base chemistry began in the 1880s when Arrhenius first defined an acid as a substance that, when dissolved in water, produces an increased concentration of hydrogen ions. Around 1900, Nouwen combined Arrhenius's definition with Faraday's previous supposition that anions such as chloride are base-forming and cations such as sodium are acid-forming. Thus, acid-base status wasn't determined solely by the concentration of hydrogen ions, but also by a number of other common electrolytes. Then in 1923, the Danish physical chemist Johannes Brønsted and the English physical chemist Martin Lowry independently developed the idea of protonation of bases through the deprotonation of acids. Thus, an acid was any compound that could donate protons, and a base was any compound that could accept protons. It was another 25 years before physicians began taking a serious interest in acid-base balance in human physiology, and when they did, they solely used the Brønsted-Lowry definition of acids and bases. Focus on the Brønsted-Lowry definition does not seem to have been the consequence of a careful analysis as to whether it actually was even the most accurate description of physiology, but may have instead been simply because it was seen as more modern than the Nouwen definition. Whatever the reason, however, attention became focused primarily on PaCO2 and the serum bicarbonate concentration as the primary determinants of arterial pH. This resulted in the incorporation of the Henderson-Hasselbalch equation into clinical medicine. As we have reviewed earlier on in this course, the Henderson-Hasselbalch equation said that the pH of a liquid equals the pKa of any acid and conjugate base pair plus the log of the ratio of base concentration to acid concentration. When applied to human physiology, physicians used carbonic acid and bicarbonate as the conjugate acid and base pair, since it was thought to be the blood's primary buffer. Henry's law was then used to convert the concentration of carbonic acid into the solubility constant times the partial pressure of carbon dioxide. Subsequently, this form of the equation has played a critical role in studying human physiology for the last 60 years. However, throughout the 1950s and 60s, healthy debate erupted over just how to best apply these new concepts to actual patients. On one side were a group of Americans based in various Boston area hospitals and led by Schwartz and Relman. On the other side were Danes Astrup and Sigurd Andersen. Astrup and Sigurd Andersen first proposed the concept of base excess as a means to diagnose acid-base disorders. Schwartz and Relman subsequently proposed a collection of prediction rules to evaluate the process of normal compensation and thus make accurate diagnoses. This is sometimes referred to as the Great Transatlantic Acid-Base Debate. At this point, let's compare these two approaches. First, I'll discuss what I refer to as the traditional approach, also known as the Boston approach, which is what I have been teaching so far in this course. When I call it the traditional approach, it's certainly not my intention to take an America-centric viewpoint, but my impression is that it is the most widely utilized approach in the world, and certainly in my home country of the United States. As already mentioned, the traditional approach as advocated by Schwartz and Relman focuses on the balance between dissolved carbon dioxide and bicarbonate ion as the primary determinant of pH. If there is a derangement in either carbon dioxide or bicarb, the body will adjust the other in order to maintain as normal pH as possible. Also, as already mentioned, the Henderson-Hasselbalch equation is key in describing the exact relationship between pH, PCO2, and bicarb, which forms the central foundation for analyzing acid-base disorders. The traditional approach defines 6 or 7 fundamental acid-base disorders, the difference due to whether one groups elevated GAP and normal GAP metabolic acidoses into the same category. A separate compensation rule for each of these was empirically derived to help determine if compensation in the presence of the primary disorder is appropriate. This was discussed in detail in Lecture 4. One criticism of the traditional approach is the fact that there is difficulty interpreting the bicarb concentration in isolation from respiratory disorders. I personally think this criticism is irrelevant, since the process of compensation makes the bicarb concentration not independent from respiratory disorders at all, and therefore it is neither desirable nor even possible to interpret it truly in isolation, irrespective of approach taken. Another common criticism, which I think is a little bit more valid, is that it fails to invoke buffers other than bicarb. As we learned in Lecture 2, there are numerous other buffers in the body, including albumin, phosphate, and hemoglobin. An alternative approach to acid-base analysis came from Denmark and primarily advocated by Sigurd Andersen and Astrup. Their approach, nicknamed the Copenhagen approach, also advocated for the importance of hydrogen balance and the bicarbonate buffer system. However, it also focused on a value called the base excess. The base excess is a measure of how far the total concentration of all buffers in the blood has been changed from its normal value as a consequence of metabolic derangements. In other words, it is a measure of how much acid would need to be added to blood to correct its pH back to normal, assuming that any respiratory disorder could be ignored. More quantitatively, it's the amount of acid in milliequivalents per liter that would be needed to add it to 1 liter of plasma exposed to PCO2 of 40 millimeters of mercury in vitro in order to restore the plasma to a pH of 7.40. It's important to realize that, like the anion gap, the base excess is an artificial construct that doesn't directly relate to an individual parameter of physiology in an actual person. It's rather a mathematical trick designed to simplify complex chemistry into something more digestible at the bedside. A normal base excess is theoretically 0 and frequently cited in practice as -2 to +2 milliequivalents per liter. A positive base excess is consistent with a metabolic alkalosis. A negative base excess, sometimes referred to as a base deficit to prevent semantic confusion, is consistent with a metabolic acidosis. The actual equation for the calculation of base excess is rather cumbersome and requires simultaneous measurement of hemoglobin, as this is also an important buffer. ABG analyzers usually will automatically calculate the base excess, sparing us the need to determine it by hand. Although this automatic calculation helps eliminate one of the biggest practical barriers to using base excess, there was another major early criticism, one that's a bit complicated to explain, but in brief, base excess is a measure of the metabolic contribution to acid-base status for just the plasma, and is a measure specifically done in vitro. Since various protein buffers exist in plasma, but not the extravascular component of the extracellular compartment, base excess may be an inaccurate measure of how much acid was necessary to truly restore the body's pH to normal in vivo. Therefore, an additional value called standard base excess was created to address this concern. Standard base excess corrects this problem by calculating the base excess with a built-in assumption of a hemoglobin concentration of 5 grams per deciliter, which is cited as a value which will give an approximately accurate result in vivo. Here is the commonly cited equation by which standard base excess is calculated. Despite my best effort, I have been unable to locate either an empirically or theoretically sound explanation for using that specific value of 5 grams per deciliter of hemoglobin. This is especially bizarre given the combination of the apparent arbitrary and inexact nature of the simple value of 5 grams per deciliter with the ludicrously exact 4 significant figures of one of the terms in this equation that is apparently used by ABG analyzers. But for whatever reason, This is how the standard base excess is typically calculated. As you can easily demonstrate on your own, for mild to moderate acid-base derangements, the base excess is approximately equal to the difference between the measured bicarb and a normal bicarb of 24. For the next 15 years, acid-base analysis didn't change too dramatically aside from a greater appreciation of the utility of the anion gap. However, in 1978, a dramatically new approach emerged. Peter Stewart, a Canadian physiologist, proposed the radically new idea that human acid-base physiology is better reflected by the earlier ideas of Arrhenius and Naumann instead of Bronsted and Lowry. Specifically, he defined an acid as any ion that shifts the dissociation equilibrium of water to higher concentrations of hydrogen ion and lower concentrations of hydroxyl ion. Through an extension of his reasoning, he rejected the notion that serum bicarb concentration was central to understanding acid-base disorders. His system of acid-base analysis is based upon 6 physiologic principles or axioms. First, as just mentioned, an acid is any species that raises hydrogen ion concentration of a solution. Second, the quantity of hydrogen ion added or removed from a physiologic system is not relevant to the final pH, since the hydrogen ion concentration is a dependent variable. Third, human plasma consists of fully dissociated strong ions such as sodium, potassium, chloride, and lactate, partially dissociated weak acids such as albumin and phosphate, and volatile buffers such as carbonate species. Fourth, an evaluation of non-volatile buffer equilibrium is important to the description of acid-base balance. Fifth, the weak acids of plasma can be described as a pseudo-monoprotonic acid HA. And finally, sixth, plasma membranes may be permeable to strong ions, and therefore transport of strong ions across cell membranes may influence hydrogen ion concentration. Using these physiologic principles, he defined 6 simultaneous equations that he believed dictated a patient's acid-base status. I won't review them individually, but will summarize by stating Stewart found a rather complicated fourth-order polynomial solution for this system of equations, which luckily can be simplified as this in most situations. You will note that the Stewart equation shares a similar form as the Henderson-Hasselbalch equation as adapted for acid-base balance. However, instead of including 2 independent variables, bicarbonate concentration and PCO2, there are now 3: SID, A total, and the familiar PCO2. K sub A is an equilibrium constant, and the S is the solubility constant for carbon dioxide in water. Let's take a closer look at these 3 independent variables. First is the SID, which stands for strong ion difference. This is the difference between completely dissociated cations and completely dissociated anions. The term strong here refers to how strongly the ions dissociate and not how concentrated the solution is. In practice, there are different subtypes of the strong ion difference. For example, SID sub A for SID apparent is used to simplify the fact that numerous minor strong ions are not typically measured, but which collectively contribute very little to this calculation. Unfortunately, there are a number of variations of the SID sub A calculation that are used in practice. This here is just one such variation. SID sub A is normally cited to be 38 to 42 milliequivalents per liter, but it depends slightly on the specific calculation used. A total is the plasma concentration of non-volatile weak acids which only partially dissociate, such as phosphate and albumin. In the absence of unmeasured anions, A total should approximately equal the traditional anion gap. Finally, PCO2 is the partial pressure of carbon dioxide in arterial blood, just the same as it is in the traditional and Copenhagen approaches. There are 2 other important variables in the Stewart approach. First, SID sub E, which stands for SID effective, represents the sum of the plasma buffers. As with SID sub A, there are several variations of this calculation. Here is one where SID sub E equals the bicarb concentration plus the concentration of ionized albumin plus the concentration of ionized phosphate. The latter two can be estimated from empirically derived equations listed here. Second, the strong ion gap, or SIG, is an estimate of the unmeasured anions in plasma and resembles the traditional anion gap, except its normal value is 0. It is mathematically equal to SID-A minus SID-E. Stewart's approach creates 6 primary acid-base disorders. First are respiratory acidosis and alkalosis, which are the same as in the traditional approach, with the exception that it ignores compensation and thus does not subdivide them into acute and chronic processes. Next is a SID acidosis, which is characterized by a low SID-A with a SIG of 0. This represents most conditions traditionally referred to as normal anion gap metabolic acidoses. Then is a SIG acidosis, which is characterized by an elevated SIG with normal SID-A. This represents most conditions traditionally referred to as elevated anion gap metabolic acidoses. Both SID and SIG acidoses are subtypes of strong ion acidosis, which are all characterized by a low SID-E. The next class of disorders is strong ion alkalosis, characterized by an elevated SID-E with an elevated SID-A and normal SIG. These represent conditions traditionally referred to as metabolic alkaloses. Next is non-volatile buffer acidosis, characterized by an elevated A total. Examples include hyperalbuminemia and hyperphosphatemia. Finally is non-volatile buffer alkalosis, characterized by low A total, as would be seen in hypoalbuminemia. There is no correlate to the non-volatile buffer acidosis and alkalosis in the traditional and Copenhagen model. The difference between the strong ion acidoses can be a bit confusing, so I'm going to clarify them a little with some diagrams. This will be most clear if I start with something a little more familiar, like the difference between a normal and an elevated anion gap acidosis, which was discussed in detail in Lecture 5. Here is a representation of normal ions in blood. On the left are positively charged cations, and on the right are negatively charged anions. The anion gap is typically defined as the difference between sodium and the sum of bicarb and chloride. In this particular example, the acid-base status is normal, and thus the anion gap is equal to 12. In the next example, there is a deficiency of bicarb and an excess of chloride, such that the total of the two remains constant, thus the anion gap is the same. This is what is seen with a normal gap metabolic acidosis. In the last group, the bicarb is again low, but instead of excess chloride, there is an excess of unmeasured anions. As a consequence, the anion gap is elevated, and thus this is referred to as an elevated gap metabolic acidosis. The difference between a SID and a SIG acidosis is very similar. We'll start with the ion concentrations seen in a patient with normal acid-base status. The Stewart model places greater emphasis on the specific concentrations of albumin and phosphate, so we will include the negatively charged proportion of these molecules in our analysis. To remind you, there are several similar equations used for the calculation of SID-A, but it is approximately equal to sodium plus potassium minus chloride, shown here. SID-E also has several equations, but is commonly calculated as bicarb plus negatively charged albumin plus negatively charged phosphate. SID-E is shown here. The strong ion gap is SID-A minus SID-E, which, as you can see from the diagram, is approximately 0. In the next example, bicarb is low and chloride is high. If we label our SID-A and SID-E, we will immediately see that the SIG is 0. Thus, this is a SID acidosis, which is practically speaking the equivalent of a normal anion gap acidosis. In the last example, bicarb is low and unmeasured anions are high. Here is SID-A, which is sodium plus potassium minus chloride, and here is SID-E, which is bicarb plus negatively charged albumin plus negatively charged phosphate. These two values are no longer equal. the difference being the strong ion gap, or SIG. Thus, this is a SIG acidosis, which is analogous to an elevated anion gap acidosis. You can also observe that in both the SID and SIG acidoses, the SID-E is reduced, which is the consistent hallmark of a strong ion acidosis in general. To further compare different approaches to acid-base physiology, I want to look at a very brief qualitative analysis of a simple physiologic phenomenon, gastric acid secretion in the stomach. The traditional approach is based on the Henderson-Hasselbalch equation. In this model, secretion of hydrogen ions into the stomach lumen by parietal cells shifts the equilibrium between bicarbonate ion and carbonic acid towards the latter. This lowers the concentration of bicarbonate ion, which by the Henderson-Hasselbalch equation must result in the lower pH of the gastric lumen. In the Stewart approach, a more complete version of the calculation for apparent strong ion difference states that it is equal to the sum of charges from sodium, potassium, calcium, and magnesium, all minus the sum of charges from chloride and lactate. Thus, it is actually secretion of chloride ion as the other half of hydrochloric acid that is important. Increasing the concentration of chloride in the gastric lumen lowers the strong ion difference, and it is this effect that lowers pH by virtue of the Stewart equation we saw earlier. I have presented a lot of information in this lecture so far, much of which will be completely unfamiliar to most viewers. Therefore, I'll summarize the lecture by presenting a comparison of the different approaches to acid-base physiology in this chart. Those three approaches, to remind you, are first the physiologic approach, colloquially referred to as the Boston approach, and which I commonly refer to as the traditional approach, which is what the previous 14 lectures have covered. Next is the base excess approach, colloquially referred to as the Copenhagen approach. Finally is the Stewart approach, which is more formally referred to as the strong ion or physiochemical approach. Starting with the physiological or traditional approach, it invokes the Bronsted-Lowry theory of acids and bases. The bicarbonate buffer system is central to the approach. The principal variables it focuses on are PCO2, serum bicarb concentration, and the anion gap. Depending on how one decides to subdivide them, there are anywhere from 4 to 7 general types of acid-base disorders, including acute and chronic respiratory acidoses, acute and chronic respiratory alkaloses, normal or elevated anion gap metabolic acidoses, and metabolic alkaloses. Historically, the major proponents of this approach have been Americans, most notably William Schwartz and Arnold Relman. Moving on to the base excess approach, this is also based on the Bronsted-Lowry theory of acid-base, and the bicarb buffer system is also central. The principal variables are PCO2, base excess, and anion gap. The general types of acid-base disorders that it defines are the same as above, and the major proponents of this have historically been Europeans, specifically Sigurd Andersen and Astrup from Denmark. From this basic chart, you can see that on a fundamental level, the traditional approach and the base excess approach are very similar. Finally, in the Stewart approach, the invoked theory of acids and bases is that of Arrhenius and Naumann. Bicarbonate is considered to be a dependent variable, and thus its importance in the approach is minimal. Instead, the principal variables are PCO2, strong ion difference, and total concentration of weak acids. There are 6 to 7 general types of acid-base disorders in the Stewart approach: respiratory acidosis and alkalosis, strong ion acidosis, which can be subdivided into low SID-A or high SIG acidosis, strong ion alkalosis, and non-volatile buffer acidosis and alkalosis. As a general rule, the Stewart approach does not usually consider metabolic compensation for chronic respiratory disorders. For example, in the traditional model, the presence of a chronic respiratory acidosis would induce kidneys to excrete hydrogen and hold on to bicarbonate as part of metabolic compensation, which would not be considered a separate acid-base disorder per se. However, in the Stewart model, this mechanism would be looked at as a reabsorption of sodium out of proportional to chloride, which would increase the strong iron difference and which would lead to a primary strong ion alkalosis that would be a separate acid-base disorder from the respiratory acidosis that triggered it. Finally, as its very name implies, the originator and strongest proponent of the Stewart approach is, of course, Peter Stewart himself. Up until now, everything I have reviewed in this particular lecture has been relatively qualitative and theoretical. This is in contrast to the previous 14 lectures, which have been heavily practical in nature. So you might rightly be wondering, how do these other approaches translate into a practical bedside analysis? That is, what is the algorithm for applying these approaches to an actual patient? Unfortunately, there are no universal and standardized algorithms. During this course, I have presented the most thorough version of the traditional algorithm that comes closest to being universal and standardized, but in reality there is still much variation from institution to institution and from country to country. While algorithms based on base excess generally reach the same conclusion as those based on the Boston or traditional approach, there is even more variation in the sequence of steps taken and the thoroughness with which the analysis is carried out. Finally, there is absolutely no standardized algorithm that utilizes the Stewart approach. In preparation for this lecture, I reviewed about 24 papers, websites, and textbooks that discuss the Stewart approach. 2/3 of these sources discuss the Stewart approach only in mathematically heavy physiochemical analysis that was far removed from actual patients, and of the remaining 1/3 of sources, every single one used a practical algorithm that was markedly different from the others. At this point, I'm going to present a real-world example of an acid-base disturbance as identified by an ABG, and demonstrate how one might use the 3 different approaches to diagnose the underlying abnormality. A 35-year-old woman presents with 2 days of fevers, chills, and a malaise. Her vitals revealed a temperature of 103 degrees Fahrenheit, heart rate of 135, blood pressure of 78/40, respiratory rate of 30, and oxygen saturation of 97% on room air. Her ABG, basic metabolic panel, and albumin are as follows. How would one use the Boston or traditional approach to analyze this situation? Step 1, check the pH. She's obviously acidemic. Step 2, check the PCO2. Since the PCO2 is low, and that is deranged in the same direction as her pH, the acidemia is caused by a metabolic acidosis. Step 3, evaluate compensation. For a metabolic acidosis, we would use Winter's formula and ask if the PCO2 is approximately equal to 1.5 times bicarb plus 8. In this case, this is true, so therefore compensation is appropriate. Step 4, calculate the anion gap, which is sodium minus the sum of chloride and bicarb, which in this case is 18. And we then adjust the anion gap for hypoalbuminemia to determine an adjusted gap of 23. Thus, the metabolic acidosis is an elevated anion gap metabolic acidosis. Then, step 5, since the anion gap is elevated, we calculate the delta ratio. As reviewed in lecture 6, this is equal to the change in anion gap from normal divided by the change in bicarb from normal. For this patient, this works out to be 11 divided by 9, or 1.2. Since the patient probably has lactic acidosis, a delta ratio between 1 and 2 is what we would expect to see, and thus there is no additional acid-base disorder present. Thus, our final acid-base diagnosis is a simple, elevated anion gap metabolic acidosis. How would we use the Copenhagen or base excess approach for the same patient? Step 1 is the same, low pH equals acidemia. Step 2 would be to calculate the standard base excess. Now there are a couple of equations in the literature on how to do this. As mentioned before, this is the most commonly cited one with the patient's values already inputted, which gives a standard base excess of negative 9.8. Luckily, most ABG analyzers will calculate this for you. A negative base excess, which is sometimes referred to as a base deficit, means that the patient has a metabolic acidosis. As with the former approach, the next step is to evaluate compensation. The base excess approach also has a collection of empirically derived compensation rules for the various acid-base disorders. For a metabolic acidosis, the PCO2 should be lowered by about 1 milliliter of mercury for every 1 mol equivalent per liter that base excess is below zero. Since that is indeed the case here, compensation is appropriate. The next step is calculating the anion gap and adjusting for albumin. I haven't included the delta ratio here since in my experience most users of the base excess approach generally don't bother with it, but there is no reason one couldn't calculate the delta ratio either by using the delta bicarb or with a slight adjustment in the equation to use the delta standard base excess. The final conclusion is the same, an elevated anion gap metabolic acidosis, and from watching these steps, you can further appreciate that on a fundamental level, the traditional and base excess approaches are nearly identical. But how could you use the Stewart approach? Remember that there is no remotely standardized algorithm to applying the Stewart approach to real-world bedside acid-base analysis. However, the following is a representation of an algorithm one could potentially use. Step 1. Calculate the total concentration of ionized weak non-volatile acids. This would approximately be equal to the sum of ionized albumin, ionized globulin, and ionized inorganic phosphate. Each of these can be calculated by a separate equation, utilizing separate constants relating the pH to the proportion of the specific molecules that are ionized. As you can imagine, this is extremely cumbersome, but take my word for it that for this patient, assuming normal levels of globulin and phosphate, the net non-volatile acid concentration is about 5 millimoles per liter. For step 2, you would calculate the effective strong ion difference. This is equal to the bicarb concentration plus A total, which is 20. Since 20 is below the normal range of SID-E of 38 to 42, this patient has a strong ion acidosis. Step 3, calculate apparent SID, which, depending upon one's preferred calculation, is approximately sodium plus potassium minus chloride. 120 minus 4 plus 87 is 37, which is nearly normal, as SID-A should also be about 38 to 42. Finally, for step 4, calculate the strong ion gap, which is SID-A minus SID-E, which is 17. As SIG should be 0, this patient has an elevated strong ion gradient. So we would diagnose this as an elevated strong ion gradient acidosis. With this example, which is actually a rather straightforward acid-base abnormality, you will probably find the Stewart approach to seem unfamiliar, non-intuitive, and cumbersome, especially with the calculation of A total, which really cannot be done efficiently without the aid of an application specifically designed for this. While I certainly do not mean this as a criticism of the man himself, I think it's relevant that Peter Stewart wasn't a physician, but rather a physiologist. For him, the lab may be the perfect setting in which he could apply his physiochemical model to work through problems in human pathophysiology. However, after working through examples like this myself, I find it difficult to believe that many people who prefer the Stewart approach are routinely in the position of needing to diagnose acid-base disturbances in real time at the bedside of critically ill patients. As an analogy, I imagine two people playing a game of billiards, and on a particularly difficult shot, one decides to use the Schrödinger wave equation to calculate the appropriate angle and speed with which the cue ball should be struck. While a person could technically use quantum mechanics to successfully play billiards, there would be no benefit over simple Newtonian physics that could be estimated in one's head, and the quantum mechanics calculations would take so long that the opponent might forfeit on account of boredom. At this point, I was originally going to review literature evidence that fails to find any measurable benefit of the Stewart approach in clinical situations, but the lecture is already running a bit long, so I will spare you. However, more compelling than this would have been is the conclusions of one particular paper, probably the most rigorous critical review of the Stewart approach, that took an in-depth look at the Stewart equation. To remind you, this equation is the final result of Peter Stewart's complex analysis of human acid-base physiology that was based on his 6 postulates and 6 equations of equilibrium and conservation. What this paper proved was that the numerator of this fraction is in fact mathematically equal to the serum bicarbonate concentration. Therefore, the Stewart equation is nothing more than a dressed-up version of the Henderson-Hasselbalch equation for the bicarbonate buffer system, the same equation that Stewart criticized as non-physiologic. In conclusion, the traditional and base excess approaches are based on similar principles and generally result in identical diagnoses. Provided that the anion gap is corrected for albumin, there is no significant benefit of the Stewart approach in actual practice. And given its lack of clinical benefits, lack of general familiarity, and its significantly increased complexity, routine use of the Stewart approach in clinical medicine is not recommended. Despite the rather strong way I've ended this lecture, the Stewart approach definitely has its advocates, and it remains quite a controversial and polarizing topic in critical care medicine. Therefore, I think it's appropriate to finish with the following 2 quotes. Peter Stewart once said of the traditional bicarbonate-centered approach, "It is cluttered with jargon, chemically meaningless derived quantities, a misunderstanding of what is happening, and an artificial use of the Henderson-Hasselbalch equation as a single equation determining acid-base balance in any fluid." While Sigurd Andersen has said in response, the Stewart approach is absurd and anachronistic. I hope you have found this lecture to be interesting and useful. The next 4 lectures will shift focus of ABG analysis from acid-base balance to oxygenation.